Hi, welcome to the New York City Category Theory Seminar. Rick Jardine is going to speak about posets, metric spaces, and topological data analysis. We're going to, I guess if you have a question, then do you mind? Do you have a preference, Rick, or anything?
Anybody can ask anytime. There'll be
Okay.
some crosstalk with the audio, but we'll see.
Okay. Anyway, so without further ado, Rick, please.
Oh, thanks, Nelson. It's a pleasure to be back at this seminar. I spoke at the New York Category Theory Seminar about 10 years ago, which I think was in the early days of the seminar.
Right. And
it's nice to be back, if only virtually. On the other hand, virtually is kind of enabling. Anyway, I have a lot of explaining to do. Let me unpack this first slide a bit. The usual thing with topological data analysis is to start with a data set that's sitting inside some ambient metric space, usually a large dimensional copy of the reals. And you look at the distances between the points in the data set and you use those distances to make spaces. These are usually simplicial complexes. And so what you do with those simplicial complexes, they're parameterized by distance, and you compare them all and see how the various topological invariants behave as you vary the parameters. So for example, if you took path components, you'd be looking at clusters, and then you'd be looking at the way clusters vary. If you keep track of all of that at once, you're looking at hierarchical clustering. If you look at higher homology groups, and you look at the way the homology groups varies as the distance parameter changes, that's the realm of persistent homology. I'm going to talk about this at the homotopy theoretic level because it sort of controls everything else as far as I'm concerned. So about those simplicial complexes, what one does to construct the so-called Vietoris-Rips complex is to take an abstract simplicial complex, which consists of a poset of subsets of the original data set, such that when you look inside a given subset, the distance between any 2 points is less than or equal to some parameter value s. Here, s can be vary between 0 and infinity. You won't get to infinity because the data set's finite. So you have these subsets consisting of points, all of which are at most s distance s apart. Any subset of those, of such a subset, still has that property. So this is, in fact, an abstract simplicial complex. Then the usual thing with that, if you go back to Sleep Spaniard's book, which is how I was trained a long time ago, is to take an abstract simplicial complex and make a space out of it called a simplicial complex. And that space is the Vietoris-Rips complex. You let S vary, and the Vietoris-Rips complexes are all compared. And you get this infinite list of spaces, or actually a finite list of spaces, like I was talking about. So anyway, you have this poset of simplices of this Vietoris-Rips complex. And you can either realize it as a topological space, that's fun, or there's another way to get a homotopy type and then a topological space out of it by this poset PS of X is a category, so it has a so-called nerve. You take the nerve of that, you get a simplicial set, and you can realize that if you want. These two approaches give you the same homotopy type because the realization of the nerve of the barycentric subdivision, I'll explain what that is has the same homotopy type as Vietoris-Rips complex. So there's no difference at all if you're just interested in standard homotopy theoretic invariants, which is what traditional TDA is all about. So of course, if distance S is less than or equal to distance T, if 2 points in the subset are distance less than or equal S apart, they're going to be distance less than or equal to T apart. So there's an inclusion of posets that reflects that, posets of simplices that reflects that. And I'm just really going to focus on this collection of posets of simplices. And so if S is 0, you're talking about the discrete set given by the data set X itself. So that's not a very interesting category. It's not a very interesting simplicial complex. It's just discrete. And if you let T get sufficiently large, you're picking up all subsets of the data set X because you've exhausted the distances. And at that point, you're picking up all of the subsets of X, and the nerve of that is contractible space. Okay, so this behavior of the posets is just like what you'd expect in the behavior of the Vietoris-Rips complexes. When S is 0, the zeroth Vietoris-Rips complex is just the discrete set X itself. when T gets sufficiently large, you pick up a great big simplex, which is also contractible. All right, so that's a basic landscape of the sort of spaces that one wants to think about usually, but one can also look at pieces, or one can also be interested in pieces of the data set that are controlled by density. So you can introduce a density parameter K, which is a number, and you look at the subposet of the simplices of PS of X, subposet of PS of X consisting of simplices consisting of elements or distance at most S apart, but have at least K distinct neighbors Y, with distance less than or equal to S from them. This is the so-called, this poset is a subcomplex of the Vietoris-Rips, corresponding Vietoris-Rips poset, and it's the poset of simplices, the so-called degree-Rips complex. Okay. Certainly, if S is less than or equal to T, the corresponding degree-Rips complex, PSK of X, is contained in PT of K of X. And if K decreases, or if K increases rather, that's you have more conditions imposed. And so there's an inclusion of degree-Rips complexes corresponding to varying the so-called density parameter K. So there's two parameters involved in these degree-Rips complex, both the distance parameter S and the density parameter K. So that poset PS of K is a poset of simplices, the so-called degree-Rips complex, the way you usually see it in literature. And the notation for that is LSKX. I used to think it stood for Lesnick because he introduced it, but he tells me he wants it called the degree-Rips complex. And again, the nerve of the poset is the poset of simplices is the barycentric subdivision of the degree-Rips complex. So those are the basic things. I haven't drawn all the pictures that one normally sees around these things. You get this big array of posets and simplices, and that's the usual realm of examples for what's called multidimensional persistence. I'm not going to get into that. Now, in some sense, the big theorem, or sorry, let me back up. I promised you a chat about what the nerve of a category is. I mean, I have these posets, they're categories in the obvious way, and the nerve of a category is, of a category C is a simplicial set within simplices given by strings of arrows of length n or equivalently maps from finite ordinal numbers n into C. Okay, where the finite ordinal number n is the numbers between 0 and n with the obvious poset structure. And composition with poset maps between these finite ordinal numbers defines the so-called simplicial structure of the nerve of C. This is a simplicial set. It's essentially a souped-up simplicial complex where you introduce a lot of degeneracies, which give you functoriality, basically, and also a good uniform description of homotopy. Examples of such things, I don't think this is talked about enough, but it's well known that if you take the poset of numbers, counting numbers between 0 and n, and take the nerve of that poset, you get this simplicial standard n simplex, because that simplicial standard n simplex is usually described as a representable functor. It's the same thing. Okay, so that's the nerve of the finite poset n. Now, if you take a group, you can identify what this is a category theory. I'm not 37. I'm not sure, how much detail I can give here. If you take a group, it can be identified with a group value with one object, right? And so that's perfectly good category theory. It has a nerve, okay? And when you take that nerve and realize it as a topological space, you get a space which has one homotopy group, namely the copy of G in pi 1, and it's trivial elsewhere, an Annenberg-MacLean space, in other words. And that is the most compact construction of that space, okay? It's the one that's easiest to understand. But the space itself in the homotopy theory, in the homotopy category, classifies principal G bundles over spaces. And for that reason, and this goes way back, B of G is called the classifying space of G. Okay, so you're going to be hearing me call the nerve of the category also the classifying space of the category, because that's where I come from intellectually. Okay, there's a big theorem And what's it about? If you have two data sets, one contained in the other, and if they're close, then the outcomes in persistent homology or homotopy invariance should also be close, and that's what's called stability. So the Rips stability theorem says the following: if you have an inclusion of data sets, finite data sets inside some ambient metric space, such that that thing that I displayed there with the d lower h, the Hausdorff distance between x and y is less than r. In other words, if every element of y has a point x in x, such that the distance between x and y is less than r, if that's true, okay, then there's a homotopy commutative diagram, so-called homotopy interleaving. This is for every S. And it says that if you take this is on a poset level, in fact, if you take the poset of simplices of poset of simplices of elements of mutual distance less than or equal to S, that includes in the poset of simplices of mutual distance less than or equal to S plus UR. Same with Y, and the outer commutative square there is no big story. The real meat of the theorem asserts that there's a map theta from the poset corresponding to S for Y to the poset corresponding to S plus 2R for X, such that the diagram homotopy commutes. Okay, that's the real theorem. And if R is small, that means that the two systems of spaces are systems of posets or classifying spaces or what have you, are very close together. You'll always see me use sigma for the map from PS of X to PT of X if S is less than or equal to T. It's usually called a shift these days, and it always seems like a suspension to me. I can't answer why. Anyway, so there's this Rips stability theorem, which is kind of the big theorem of the last 10 years, and the big theoretical theorem of the last 10 years in topological data analysis. And that's because it's true on the homotopy level. So you have this homotopy commutative diagram of functors between posets, and I'll explain why that's homotopy commutative. And it induces homotopy commutative diagrams on the space level, whether or not you take the Vietoris-Rips construction or the nerves of posets. And so you get a corresponding induced diagram in homology groups. So you get homology stability for all degrees K for all fields in the coefficients. Okay, and that's what gives you the classical stability results in topological data analysis that people used to express in terms of barcodes and so on. So this homotopy assertion is giving you the homology stability, but it also gives you a corresponding statement for path components. Path components, say a VS of X, that's a cluster in the data set X, and the stability statement for path components is giving you a statement about clusters as well. Okay, this thing has a proof. Let me just sketch it. Suppose I give you an element of the bigger set Y, and then the condition means that there's an element close to it in X whose distance is less than R. R is a specific number. So I'm going to call the element in X which is close to it theta of Y. If X started life inside X, I can just let theta of X be X. That gives me a function from Y back to X, okay? Now, if Y1 and Y2 are elements of Y which are distance less than or equal to S apart, well, theta Y1 is distance less than R from Y1, and theta Y2 is distance less than R from Y2. And then the triangle identity tells you that theta of Y1 is distance less than S plus 2R from theta of Y2. See, that's why this function theta that I described induces a map in the poset level. All right. Now there's another trick. So let's start with just some element of PS of Y. In other words, a collection of elements which are distance less than or equal to S apart. And I apply this function theta to it. I get a bunch of elements S, and I can take the union of those two sets inside Y. And that's a picture of it. Now, there might be repeats in the list that I've given on the board, but you remove them. And so you have this union subset, sigma union theta of sigma, and the distance between any two elements in there is less than or equal to S plus 2R. Okay. And so there's inclusion, segment into the union, and also theta segment, that's subset into the union. And those are natural transformations between poset morphisms. Those are homotopies. And that's what's giving you the Rips stability theorem. All right. So what about these homotopies? I said natural transformation. Well, a natural transformation, if you look in any book in category theory at all, you have functors from F and G from category C to category D. And a natural transformation between those things is a set of morphisms, H from FA to G of A, one for each A in the category C, okay? And you want the corresponding square diagram involving the action of F and the action of G to commute with all of these choices of morphisms H. Well, I think I learned this from McLean's book way back when, that a natural transformation like that is the same thing as a picture like on the left in terms of functors. A natural transformation is a functor from C cross ordinal number 1, two elements 0, 1, 0 less than or equal to 1, from C cross 1 to D. All right. That's what natural transformation is. And so there's a commutative diagram like you're seeing on the left of functors. I sub 0 takes an object C to the object C comma 0 inside C cross 1. And I sub 1 takes C to object C1 in C cross 1. And so they're the same. Okay, so you got a picture like that on the left. When you apply the nerve construction to it, you get a corresponding picture of a corresponding commutative diagram of simplicial sets. And when you take the nerve preserves products, so the nerve of C cross ordinal number 1 is isomorphic to the nerve of C cross B of 1, which is nerve of C cross standard 1 simplex. And so you get a classical simplicial homotopy out of this natural transformation when you apply the nerve construction. This kind of thing's been known for a long time, but it really got used heavily starting with Quillen's introduction of higher algebraic K-theory back in the early 70s. So this is where this is the beginnings of categorical homotopy theory, and that's where it comes from. All right, so going back to that picture, you see those two natural transformations are giving you homotopies between maps from nerve of PS of Y to nerve of PS plus 2R of Y, and that's giving you the stability theorem, or the statement of it. Okay, well, there's a corresponding thing for these degree Rips complexes. Again, you're looking at the finite subsets of a metric space Z. Z's usually huge. We have an inclusion of finite data sets sitting inside Z, okay? And now you insist a slightly more interesting relationship between, on the Hausdorff distance between two spaces. I'll explain in a second. If that Hausdorff space between those, if that Hausdorff distance between those two spaces is less than R, then there's a homotopy commutative diagram on the poset level for this comparison of degree Rips complexes, okay? And again, it gives you a homotopy commutative diagram of the corresponding simplicial complexes, and it's a stability theorem for the degree Rips complexes subject to this condition on the Hausdorff distance between these sets. What are these sets? X upper K plus 1 sub DIS means sets of K plus 1 distinct points in X, okay? And certainly the sets of K plus 1 distinct points in X sits inside the sets of K plus 1 distinct points in Y. And both of them have metric space structures that they inherit from the K plus 1 product, K plus 1 full product of Z with itself, okay? So we have metric spaces. This guy and this guy sitting inside metric space of K plus 1 fold, or the metric space given by the K plus 1 fold product of Z. And this is now a condition on the Hausdorff distance, meaning that every set of distinct K plus 1 distinct points has a set in Y rather, has a K plus 1, a set of K plus 1 distinct points in X, which is close to it, okay? And so the proof of that, it's now only about 16 months old, follows the same pattern as you saw before. It's strictly a poset argument, even though it's slightly more involved than the last thing was. Okay. All right, so let's just pretend the Vietoris-Rips complex or system is actually the thing that you get out of these nerves and posets, okay? That's okay in the homotopy category, that's fine. So the reproducibility theorem tells you when you get a so-called homotopy interleaving between the Vietoris-Rips complexes. In other words, a homotopy commutator diagram that looks like this thing here. Okay, so let's suppose you have that. If you have two elements in the path components, let's see, the Vietoris-Rips complex card. Okay, if you have two path components in the Vietoris-Rips complex corresponding to parameter S and X, then you can map them to the Vietoris-Rips complex corresponding to Y. And if they have the same image as path components, then you have two things going to the same thing in path components here, but then they must go to the same thing here, all right? So if class X and class Y have the same image in the path components of Vs of Y, then they have the same image in the path components of Vs plus 2Rx, okay? So I would call such a thing a 2R monomorphism. If two things go to the same thing in Y, then they go to the same thing after a shift, and the shift you can predict is 2R. Similarly, the induced map from path components of system corresponding to X to path components of system corresponding to Y is a 2R epimorphism. If you have a path component for Vs of Y, and after shifting 2R times, it's in the image of the path components corresponding to Vs plus 2R of X, okay? Just by the commutativity of this diagram, or the homotopy commutativity of this diagram. So the map, if you take all these guys together, it's a diagram of spaces. And if you compute path components, you get a diagram of sets. And you have a comparison of diagrams of sets induced by the inclusion of X and Y. And on the level of path components, and that comparison of diagrams of sets is a 2R monomorphism and a 2R epimorphism. I say that's a 2R isomorphism or bijection. All right. And you can play games with higher homotopy groups as well. And you see that in homotopy groups, all the induced maps from nth homotopy groups that you see for the various Vs of X to nth homotopy groups corresponding to the various Vs of Y, those are 2R isomorphisms as well, because the diagram homotopy commutes, but homotopy commutes in a nice way, which makes that easier to prove. So this sort of statement about 2R isomorphisms is true for path components in all higher homotopy groups. And that's what I mean when I would say that the induced map from Vietoris-Rips system for X to Vietoris-Rips system for Y is a 2R equivalence, okay? All right, so we'll generalize that. Now I've been saying system of spaces. By that I just mean a functor. System of spaces is a functor on this poset taking values in simplicial sets, okay? The Vietoris-Rips complex construction is exactly one of those. I say system of spaces to be friendly. Normally I say diagram of spaces, and somebody might say pre-sheaf of simplicial sets, but that would be bad behavior because there's no topology around that works here. This is a completely functorial thing. So the system of spaces is just a functor, and a map of systems is a natural transformation. So it's a category of such things, and I've given you the standard notation for it. You know, functors from, say, I to Y is usually represented as C to the upper I. So in this case, the target is simplicial sets, and the index category is this poset. Okay, so you roll the tape. As you lay S vary, you get a functor taking values in simplicial sets. That's a system of spaces. And this is such a thing for any data set sitting inside some metric space. And if you have an inclusion of data sets, then the induced map of the corresponding posets and spaces, they define maps of systems. It could be systems of posets if you're just interested in the posets, but also spaces if you take care of. Okay. So that's the sort of functorial, or that's the sort of big picture construction of what's going on with Vietoris-Rips and its relatives. These things have homotopy types, and they've been understood for a long time. So there's various homotopy theories of these systems, or diagrams of simplicial sets. And the oldest is the so-called projective model structure of Buzzkill and Kahn, first appeared in their book in 1972, although they don't call it a projective structure. They don't call it a they may not call it a model structure. I don't think Quillen's homotopical algebra has been around so long then. And so a map of systems is just a natural transformation. You say it's a weak equivalence if it's a weak equivalence for each parameter value S. And the corresponding map of simplicial sets, it's a weak equivalence for each parameter value S. And you say it's a fibration if each of the constituent maps is a fibration of simplicial sets, which means confibration. And we don't need to know what that is right now. All right. But then you have weak equivalences and fibrations, and you're hoping for a model structure maybe, and there is one. This is so-called projective model structure. And so, in all such cases, cofibrations are defined by lifting properties. So a map from system A to system B is a so-called projective cofibration if it has the so-called left lifting property with respect to all maps, which are fibrations in each section. Weak equivalences in each section. That's what the trivial fibrations mean there. And you can prove, just for a little recreation, that if you have an inclusion of data sets, then the induced map in Vietoris-Rips systems is a projective cofibration. Okay, there is actually something to prove there, but it's not tough. Now that map is a projective cofibration. Well, for various reasons, it's also an inclusion of simplicial sets. In other words, a cofibration of simplicial sets in each section, well, for each parameter value S, so that all the maps, induced maps induced by the inclusion between these Vietoris-Rips complexes are monomorphisms. I'm talking about simplicial sets at this point. So I would say that such a map is a section-wise cofibration. That's from my pre-sheaf days. And from my categorical days before that, after having read McLean's book, he used to call such things point-wise cofibrations. Okay, so there's these various things in the literature. And one could say that fibrations and weak equivalences for this projective structure of Buzzkill and Kahn are defined section-wise, in other words, or point-wise. Okay. So that's the ambient thing that's going on. I'm not going to do anything more sophisticated than this because I don't have to. But there's many, many model structures for this. Okay. So I had these interleaving diagrams, these the homotopy interleaving diagrams that arose from conditions on Hausdorff distance on data sets, one sitting inside the other. And I told you about the outcomes. There was these 2R bijections that happen in all degrees in homotopy groups. And so I say that a map is an R equivalence of systems. Remember, these are functors. If the induced map of systems of sets is an R isomorphism of systems of sets. Okay? In other words, it's an R monomorphism and it's an R bijection or an R surjection. That's on path components. And on higher homotopy groups, you want all of the corresponding maps of higher homotopy groups to be R isomorphisms of systems of groups. But you have to be a wee bit careful about choices of base points. You choose all of them because not all these simplicial sets on a system might share the same vertices. Okay, so you have to be able to pick your vertices wherever you find them. So a map of systems in general is an R equivalence if it's an R isomorphism of path components and R isomorphisms of systems of higher homotopy groups. Somebody's phoning. Oh dear. Okay. So that's what our equivalences are. And if I give you a diagram, I mean, there's various observations you can make. If I give you a diagram of systems where the vertical maps are section-wise equivalences, then F1 is an R equivalence if and only if F2 is an R equivalence. That's easy to prove, okay? And the basic examples of these things come from stability results, like I told you. But there's also this notion of section-wise equivalence. That's a map which is a weak equivalence for each parameter value S. But that's just a zero equivalence, you see. So all these things fit into this rubric of R equivalences as R varies. So I say that a controlled equivalence is a map which is an R equivalence for some R greater than or equal to 0. But the game here is to control this R, okay? So let's go on with that. You don't get a triangle identity like you're used to from homotopy theory on the nose, okay? So let's just read one statement here. If F is an R equivalence and G is an S equivalence, then H has to be an R plus S equivalence, okay? If F is an R equivalence and H is an R S equivalence, then G has to be an R plus S equivalence. I mean, and so on. So if two of these if one of these maps is an R equivalence and one is an S equivalence, then the third has to be an R plus S equivalence. And that's the proof of just set theory, okay? You use chase elements. So that's easy to prove. Something that's trickier is that you want to show some sort of push-out statement about our maps which are both section-wise cofibrations, then our equivalences. And the theorem that you end up proving is that if you have a push-out diagram of systems such that I is a section-wise cofibration and an R equivalence, then the push-out is a section-wise cofibration. That's easy, but it's a 2R equivalence, okay? That's actually a fairly tricky theorem. It involves a calculus of fibrations, which you have to work at a bit to get. And the proof of that involves first proving something that looks like a Whitehead theorem in this context, namely that if you have a cofibration, which is an R equivalence, then you construct a fibrant model of it in the section-wise fibrant model of it, and you can show that there's an R, 2R interleaving like that once you've taken care of being careful with fibrations. So that's what I mean by Whitehead theorem. Then these things push out, and that gives you the theorem. Okay, so it's kind of non-trivial. And the things you have to do with fibrations are sort of adjusted versions of the things you do classically with fibrations of simplicial sets. But the point is, as soon as you do something, you end up having to change the R to 2R, okay? And that's how it goes. I'm not going to prove this here. It would take too long. Okay, put it all together, you get a version of the category of cofibrations for both the projective structure and also for both projective cofibrations and then section-wise cofibrations. They are slightly distinct. Okay, so people that are up in their classical homotopy theory will know that there's a set of axioms around which defines a category of cofibration structure for homotopy theory, okay? And that's what's going on here, except we had to adjust. As I said, that the triangle axiom, you have to change it. So it's not the case that if you have A to B being an R equivalence and B to C being an R equivalence and A to C is an R equivalence, it's a 2R equivalence, okay? So you have this adjusted statement that I wrote down before. The composite of two cofibrations is a cofibration, that's easy. And then the isomorphism is cofibration, that's easy. And cofibrations are close under push out. Again, that's easy. But the hard thing that I told you about, or the interesting thing rather that I told you about, is if you have a cofibration and R equivalence, then it pushes out to map, which is a cofibration and a 2R equivalence. Okay, and you might recognize that these are altered versions of axioms that you've seen in books. It's a few more. For any object A, there's at least one cylinder object. That means A cross standard one simplex, and all objects are cofibrant. So this works for both projected cofibrations and section-wise cofibrations. And it's an adjustment of a category of cofibration structure that I call persistent homotopy theory now, okay? And I concentrate on the cofibrations because I think that's liable to be of most use in practice, okay, whether or not you believe the homotopy theory. But those axioms have standard outcomes that, again, you find in books. For example, the so-called left properness statement. You have a push out of an R equivalence along a cofibration, and you get a 2R equivalence. Again, you've done something there, so you had to double the parameter by, you had to double the parameter. And there's also a patching lemma. If you know what the patching lemma is, you have weak equivalences on two parts of, you have a comparison of push-out diagrams, you have weak equivalences on the input data, then you get a weak equivalence on the output data. But this patching lemma here says that if you have R equivalences, comparing the two push-out diagrams, then you get 8 R equivalents on the corresponding push-out. So that's almost kind of a joke almost, because that's not what you want to see when you're writing algorithms. But anyway, that's what the structure is. All right, time. Now, this is all very nice, but maybe we started out the theory in the wrong place. Let me show you how to change that a bit. I'm talking about metric spaces, but if you look at Spivak's, I think it's 10 years old now, his preprint on simplicial fuzzy sets, he talks about these extended pseudo-metric spaces. And I'm just going to call them EP metric spaces because I don't want to see extended pseudo every time, okay? So an EP metric space is a set with a function taking values in the interval between 0 and infinity. Note the infinity is in there now, okay? Such that, you know, any element is distance 0 from itself. There's the symmetry property. It's certainly a triangular inequality, okay? But the difference is that you can have distinct elements which are distant 0 from each other. That's the pseudo part. And you can have elements U and V which are infinite distance from each other. That's the extended part. Every metric space is an EP metric space. You just compose with the obvious inclusion, you know, of this half open interval into the closed interval. And so this is a bigger context than metric spaces. And so we're going to talk about finite EP metric spaces rather than finite metric spaces in the sequel. There's a category of such things. A morphism of EP metric spaces is a function which is non-expanding in metrics. In other words, the distance between f of x and f of y is less than or equal to the distance between x and y in x. All right. And I write EP met. That is supposed to be bold font. Didn't come out that way for the category of these spaces, these extended pseudo-metric spaces and their morphisms. Okay. Why would you care? Well, there's a quotient construction. If I give you an extended pseudo-metric space and a surjective function onto something, I can construct an extended pseudo-metric space structure on Y, which satisfies the obvious universal property. And that metric is the metric that you impose on Y is interesting. The distance between X and Y is an infimum of sums of distances between comparison points in X, such that X naught maps to X. I have K elements here, K pairs here. X naught maps to X under P, XK maps to Y under P, and P of Y of I is the same thing as P of X of I plus 1. So these intervals, if you like, coalesce inside the quotient. And you look at an infimum of all such things. These are what I call polygonal paths. And note that if X is finite, then Y is finite. And so that inf will be, it will be reflected by some particular path. And one uses that. Now, this is an infimum or minimum over polygonal paths, certainly for X. I'm sorry?
Oh, so basically it's like a geodesic distance.
I'm sorry?
I'm just saying, it looks like, so basically it's like geodesic distance.
Yeah, it is a bit, I guess. Yeah, I'll carry on. This is kind of a new thing here. So we'll see. So if you have X and Y sitting in X, you know, that just the pair XY itself is a path from X to Y. So it has a certain length. And so this distance, as you define it, is an infimum along all such paths. And so the distance from P of X to P of Y is less than or equal to the distance from X to Y. Well, this distance induces an EP metric space structure on Y, and that's what I've just told you is telling you that the map P is not expanding. So it's actually a map from the EP metric space X to this newly constructed EP metric space Y that you get out of a set theoretic quotient. These polygonal paths concatenate, so the triangle identity holds, and well, distance from X to X, 0 just is, and the relation is symmetric too, because you can go back along paths. And in fact, this quotient map now satisfies the universal property. Okay, it's the obvious universal property. This is kind of the really big thing about these sorts of metric spaces. This quotient construction. Let me tell you why. Suppose I give you a big collection of EP metric spaces, okay? Take the disjoint union of the underlying sets. I can construct an EP metric on that disjoint union, which just restricts to the metrics on each of the summands, but where each point in xi is infinite distance from each point in xj if I is not equal to j. I may have muttered something earlier about this infinite distance being good at picking off path components, and this is exactly why. Okay, so there's this new EP metric on this disjoint union of copies of various EP metric spaces. And this thing just wouldn't exist in metric spaces, right? Because you require infinite distance. This construction gives you the coproduct in EP metric space, and that quotient construction I just told you tells you how to put an EP metric on the set theoretic coequalizer of two maps, such that you get a coequalizer in EP metric spaces. So that means that this category is co-complete, okay, because it's got coequalizers in all disjoint unions. And again, that's an old thing we all know from category theory. Okay, so that co-completeness is good for things. Let me give you an excision result. Okay, let's suppose I give you two subsets of a finite metric space set, all right, such that as a set theoretically Z is X union Y. Okay. Well, X and Y are EP metric spaces, so as their intersection, you can form the push-out in EP metric spaces, and that's what I mean by this push-out notation that I'm running my cursor under there. And certainly there's a canonical map to the metric space Z that's induced by the two inclusions of X and Y. It's the identity on the underlying point set, but the metric's different. Namely, you can show that the distance between X and Y is an infimum over all sequences, X equals X naught to XK equals Y, and you look at the sums of the distances between the successive points. Okay, it's the infimum over all those guys. Again, if X and Y are finite, this infimum is realized by some particular path or some particular sequence of points. All right. Well, if 2 points in this X union Y, this set, are in the same path component of the Vietoris-Rips complex corresponding to parameter value S in X, Y, what has to happen? Well, it's a collection of polygonal paths in this cut product here, but they each break up into polygonal paths which are in either X or Y, because they're simplices which are in either in X or Y. And what that tells you is that the induced map and path components of the union of the Vietoris-Rips complexes corresponding to X and Y to the path components of this Vietoris-Rips complex corresponding to this EP metric space. That's an isomorphism. That's an excision result in the classical algebraic topological sense. You construct these Vietoris-Rips complexes for these EP metric spaces in exactly the same way I told you to construct them for ordinary metric spaces, right? You have parameters, distance s. It's just now that the parameter s equals infinity matters. But you have this bijection, whereas I don't know about you, but there's been a bunch of times that I've wondered about the relationship between the path components of Vietoris-Rips for Z with path components for the union of simplicial sets, and they're not the same. But this Vietoris-Rips or this EP metric space push out gives you the right answer. Now that's just for path components, and if you just care about clusters, that's fine. But I don't know a statement about higher homotopy or homology groups. Now, that's something for somebody to think about. Is there a excision result for persistent homology like this? That's a question you could ask. We certainly have it for clusters. Okay. Now, this will be looking a little more appreciative. We have this diagram of functors from poset of numbers between 0 and infinity to simplicial sets. Okay, these are just diagrams indexed by that particular poset. Now suppose that I give you a simplicial set K and an element S between 0 and infinity. Well, there's a representable object corresponding to that, which is, again, one of these diagrams, but it's specified to be K if T is greater than or equal to S, and it's just empty set if T is less than X. And this is exactly the same construction as you'd use for a representable object in Appreciates, for example. And exactly the same proof. You can look at homomorphisms from one of these representable guys to X. That's the same thing as simplicial set maps from K to the S sections of S, okay? And that's for any diagram, X. So a simplex of S is just a morphism from one of these representable guys to X. And what that is an n simplex of the S sections of S. Okay. And a morphism of simplices is a commutative diagram. See where I'm going with this? There's going to be a simplex category. And that commutative diagram translates into a commutative diagram that you see here. Okay. S has to be less than or equal to T for this to make sense. Okay. And simplex category is the category of simplices in all such commutative diagrams. This is for a diagram of functors. And I denote it in a suggestive way because that's the way I denote simplex category in simplicial sets. Okay, there's a realization constructor from this category of diagrams in simplicial sets to extended pseudometric spaces. And you do this almost by cheating. There's a metric space structure on the set of elements between 0 and n such that the distance between I and j is s. Now you can cook that up any way you like. You can take axes, and or you can take standard basis vectors and multiply them by the right thing to get such a set. If you have a poset map from ordinal number m to ordinal number n and s is less than t, then theta induces an EP metric space map from this metric space to that one. And that works because the distance between theta I and theta j is less than or equal to s, but that's less than or equal to t. And that's the distance between I and j. Okay, so this is a perfectly good EP metric space map. And it's functorial in its description. So you can define an assignment, rather a functor, which takes the simplex of this diagram X to the corresponding space UNS. Okay. Okay. And that defines a functor from the simplex category for X to extended pseudometric spaces. Then the realization of X is the co-limit of that functor. Okay. Just like it was for simplicial sets. The realization of a simplicial set is a co-limit of topological standard n simplices indexed over the simplices of the simplicial set X. It was automatic back in the day that the realization functor had a right adjoint, namely the singular functor. And that was the first known example of an adjoint pair of functors. That's where the term came up. That's where it was invented. And this singular functor from extended pseudometric spaces to diagrams, it's right adjoint to realization the way I've defined it by this co-limit. And that's no accident. Okay, so you have functors, realization from diagrams of simplicial sets to extended pseudometric spaces, and it has the right adjoint from extended pseudometric spaces into diagrams of simplicial sets. Well, that seems kind of strange. That's the way it is, and this is in Spivak's paper, although he said it in a different way. Okay, so the question is, what is this realization? What does it actually do? And so I start with a diagram. Now the these co-limits are always set theoretic co-limits with funny metric space structures, okay? So co-limit of the simplices set theoretically, it's just the value that the diagram takes at infinity. In other words, it's the co-limit for the whole diagram, because infinity is terminal in that poset. So that's the underlying point set, simplicial point set. And so you start with such a diagram, construct the realization, and the question is, what's the metric on that? And the metric between 2 points in any simplicial degree is defined to be an inf over sums of these numbers SI, where the SI, it's indexed over polygonal paths and simplices corresponding to various parameters S. Okay, so the simplex the polygonal path consists of one simplices in XSI, and you want X naught to go to X, X to go to Y, and YI and XI plus 1 to have the same image in X infinity. And that's the metric. That's what the co-limit construction in an EP metric spaces is telling you to write down after you've thought about it a while. This took me a bit of time to prove. Okay, so this realization has a nice form. And so we have examples. If I give you a totally ordered finite EP metric space, then I can write down the Vietoris-Rips complex in a nice way using that ordering. In other words, I take Vs of x to be the simplicial set with n simplices given by strings of relations written that way between the various elements. Well, if you think about it, any subset of x consisting of elements distance less than or equal to s apart, well, that subset has an ordering that it inherits from the ordering on x, and that gives you these relations. Okay. So that's what Vietoris-Rips as a simplicial set in the presence of a total ordering, and this is what any of these simplicial complex constructions from days of yore would be like in the presence of a total ordering. So total ordering becomes kind of important, although you can always cook one on. You can always cook one up, right? Because we're talking about data sets, and data sets are lists. So there's a total ordering for you. But the question is, how do they come up in a more subtle way, such as in the presence of a time series? Okay. So we got this, in this presence of total ordering, we got a canonical description of Vietoris-Rips. And again, this the nerve of the poset of simplices is barycentric subdivision. Now, if X is totally ordered finite EP metric space, then the realization is going to be an EP metric space again. The realization of the Vietoris-Rips simplex is just X itself. And that's the way, that's because of the way the distance on X infinity, which is just X, comes up. I'm not going to go through it. It's easy. So the realization of the Vietoris-Rips complex is the EP metric space, which is just the EP metric space you started with. That's the point there. Okay. So I told you that realization was right adjoint or I'm sorry, I told you that the singular functor was right adjoint realization. So again, you crack open McLean's book, and there's a co-unit construction for that. There's a co-unit map associated to that adjoint pair from, say, the Vietoris-Rips system associated to X to the singular functor applied to the realization of that Vietoris-Rips system. But the realization of the Vietoris-Rips system is just X itself. And so you end up with a canonical map from the Vietoris-Rips system corresponding to X to the so-called singular complex. All right. And you can say what that map beta is. It takes a simplex, which is an ordered tuple, to the simplex that you, or to the sequence rather, that you get by just forgetting the orderings, okay? Because on the right-hand side, you're just talking about maps from these UNs of S's to X, and you're just picking up sequences of elements in X, you know, distance less than or equal to S. All right, so you take an ordered sequence and forget about the ordering. Now this sequence of elements is sometimes called a bag of words because you see things like that come up in the context of studies of language structure with topological data analysis. That's where it came from. Okay, so you're forgetting the ordering, but it doesn't matter because we have a theorem that says that this canonical map for a totally ordered finite EP metric space is a weak equivalence of simplicial sets for all distance parameters S. Okay, again, this is a non-trivial result. The proof uses old stuff that I know from simplicial approximation theory. There's two steps to the proof. You show that the comparison of posets of non-degenerate simplices of VS to non-degenerate simplices of the singular thing induces a weak equivalence on the associated nerves. And you do that with the sort of proof that I showed you for the stability theorem, the Rips stability theorem. In other words, you construct a map backwards, and the way to construct a map backwards is you take a sequence and take it to its set of distinct elements, okay? And that gives you a perfectly good homotopy equivalence of posets. This second part of this, there's a canonical map from the what's called the subdivision of the simplicial set SX. The simplicial set of the singular complex, and it takes values in the nerve, the poset of non-degenerate simplices of the same simplicial complex. That's an isomorphism. If you started with the simplicial complex, or, you know, this is a general thing. The map from SD of K to Bn of K is an isomorphism if K is a simplicial complex. But for arbitrary simplicial sets, that's a little more interesting. What you have to show to prove something like that is to show that each subcomplex of this singular object, which is generated by a non-degenerate simplex, is contractible. Okay? And that's what you do. But ultimately, it's just categorical homotopy theory again. It's not a big deal. It's just you have to put it together in an interesting way. So that's what you get. You have the singular complex construction, which is putatively not the same thing as Vietoris-Rips, but it's weakly equivalent, so it's okay. And this is true. Totally ordered finite EP metric spaces. Totally ordered, yeah, finite EP metric spaces. What time is it?
It's it's 8:02.
If I whip through this in 5 minutes, would that be okay?
Perfect.
Okay. There's this UMAP construction due to Helium McInnes, work at Tut Institute that some of you may have heard of. It's a fast way of computing path components, or a fast way of computing clusters in particular cases. And it's described in an interesting way in terms of simplicial fuzzy sets. But I want to show you that you don't need the simplicial fuzzy sets, and you get something that's perfectly reasonable to think about. It involves changing the distances that you see in an EP metric space, or not. But anyway, what you do is you take each element of a set, of a data set, and choose a set of neighbors nearby. Okay, this is what I'm calling n sub x. It's a finite set of neighbors. And I set r sub x to be the maximum distance from x to one of its neighbors inside this n of x. Okay, we'll come back to that later. Now, if you take each member of n of x, there's an array from x to y, just x and y itself. That's a finite EP metric space. So you can take the wedge of those rays in EP metric, in EP metric spaces along the common element x. So that's what this wedge notation means, but it's in EP metric spaces. So that's forcing certain things on you. This is a co-limit in EP metric spaces of a bunch of rays. Okay. Well, the distance from x to y stays the same, but the distance between outer ends of these rays, well, it's interesting. You have to go down to x and back up. Okay. It's forced on you by the description. Okay, so we have this EP metric space structure on U of x, which consists of x and all the elements in a set of neighbors. And you can extend it to an EP metrics on all of x by just insisting that distance between any 2 points, when we're not both of them are in U of x, is infinite. Okay, you can do that. Perfectly good thing. Again, that's done just with formal nonsense. Okay, so that gives you a metric d sub x on all of x, which is defined by the neighbors of x. Okay. But you can take a disjoint union. Well, I mean, you can think of x as a great big disjoint union consisting of infinite distances between them, right? And the inclusion of x inside each of these v's is a perfectly good EP metric space map because it reduces distance, right? I mean, and the distance is infinite, it's easy to reduce it. Okay. And so you have this collection of inclusions of x into these new gizmos. So you have these EP metrics on x, d sub x. You take the corresponding Vietoris-Rips complex associated to it. You have this inclusion of systems of spaces from a discrete space into Vx dx. And now you take the iterative push out of all of these inclusions over x. Okay, so it's like gluing a whole bunch of simplices together along a discrete space, namely x. And this is what one calls Vxn. In the Helium-McInnes paper, where this was first discussed, they discussed it in terms of, well, simplicial fuzzy sets, and they used Spivak's constructions. And so they wrote it down as this, not quite, but they wrote it down as this iterated disjoint union or iterated push out of all these copies of the singular functor over the vertices, but you can replace it by this thing involving Vietoris-Rips, which is much easier to get your brains around. Now, Helium-McInnes also rescale the metrics, but I'm not going to do that here because really rescaling doesn't change much about the big picture. And this diagram here, this system is what I'm going to call the UMAP complex. This is the basis for the UMAP algorithm, the way it was implemented by Helium-McInnes. And the game here is to figure, well, the game here is to figure out what it was, first of all. I've done that. And the second part of the game is to figure out why it works so well. We're not quite there yet. Okay, so you go through all of this to construct this new system spaces, Vxn. It depends on the set of neighborhoods, choices. And then you apply the TDA machinery to that. It's a system of spaces, so you can talk about path components and homology and so on. Mostly the interest has been in clusters, but that's why they use path components to talk about these things. So apply TDA machinery to this new gadget. And there's various comparisons you can make, starting abstractly with a totally ordered finite EP metric space with a set of neighborhoods. And you construct this Vxn. There's a canonical map to the Vietoris-Rips system associated to X. Okay, because there's a EP metric space maps that created. And inside V of X, there's a graph. Well, let me back up. I got ahead of myself. You can look inside X, the data set. You can see that a pair of elements is a neighborhood pair if X is in the neighborhood for Y or Y is in the neighborhood for X, okay? You make a graph out of that with vertices X and edges given by all neighborhood pairs. It's not just a graph, it's a system of graphs, right? Because S is varying here. The distance parameter is varying. And you can prove a lemma, namely that the path components of this UMAP complex for distance parameter S are isomorphic to the path components, piece of the graph, the neighborhood graph for parameter S. Now, these aren't directly comparable by a map. You have to show that they do the same thing to the set of vertices. Okay, but they fit into a commutative diagram. And if it's the case that all the one simplices of Vs of X are neighborhood pairs, then the vertical map I star is an isomorphism. This will happen in a totally ordered EP metric space, totally ordered, when you define n of x by k nearest neighbors the way helium mechanists do. You take r of x to be this maximum distance from x to all the points in its set of neighbors. And you take this number s to be less than r of x for all s. That means everything in distance less than s is in this set of nearest neighbors. So you get an isomorphism there in that case. And so for s less than all these rx's, you get this canonical map from Vxn to Vx induces isomorphism in path components. Okay. But after that, things get weird. Because you can look at what this UMAP complex converges to, what happens at the parameter infinity. And what turns out is that the space you get is a big wedge of circles. It's nothing like contractible, although it is connected. If you just care about clusters, that's cool. And you can just do that with classical algebraic topology. I won't bore you with the details, but basically, this iterative pushout is an iterative pushout of contractible spaces over a common vertex set. You can collapse one of them to a point you haven't messed up the homotopy type of the iterative pushout at all. And so one of the components goes away, and that means that you're contracting the sets of vertices and all the other things that are involved. And each one of these is a suspension of the discrete set n, where you've assigned a base point to some element. You may as well be 0. And so this is a suspension of a wedge of n copies of S naught, and that's just a wedge of n copies of S1. Do that for every n, and you get this relation. Namely that the space that comes up in infinity is a really big wedge of circles, okay? So that's where we are now, and we'll see where we go from here. Thanks very much.
Okay, thank you very much. That was very nice. Any questions?
Durette?
I don't think anybody's forcefully muted.
I think you can all unmute if you want.
Say again?
You can all unmute if you want.
I think that everybody is unmuted.
Great, thank you. I just wanted to ask one question about the big wedge of circles that ends up. It reminds me of like sphere bundles overlaid as fiber contractions. Is that somewhat close?
Maybe it could be made up to look like that, but this is just sort of a hands-on construction of the homotopy type. So.
Right, because it's the category. Okay, yeah. Thank you.
You're just spending a bunch of copies of S naught, which is what, I mean, a wedge of a bunch of copies of S naught. That's what a discrete set looks like in the pointed homotopy category, right? So. That's pretty easy. There's nothing fancy there.
How computable is your construction of the UMAP complex?
Well, we'll see. I think this has to be tried out with algorithms. I mean, helium mechanists use the singular functor to great effect in their algorithms, right? But the Vietoris-Rips construction is much simpler. And this graph that I'm talking about is simpler. Again, in fact, I think it's very small. So we have to make some experiments now to see what's going on here. I think the fact that that graph is very small relative to the Vietoris-Rips system is what makes the calculations, the path components so effective. But I don't know about computational complexity or anything like that. It's a fairly new result.
Okay. Any other questions?
Just one more. Near the beginning, there was talk about a one-cylinder object and the patching lemma, and there was 8 equivalences that popped out at some point, and
Yep.
it was brushed over as not important. But I just wanted to maybe get like a little snippet of how those pop out from the pseudometric space.
This is, I mean, the formal proof of the patching lemma involves a bunch of moves, right? And it turns out there's 3 of them, and that's where the 8 comes from, because every time you make a move, you have to double by 2. Okay.
Ah, okay. Thank you. That's good.
Is there time for a quick question?
Please.
Do you know anything about the stability of the UMAP?
I'm sorry about that.
Do you know anything about the stability of the UMAP filtration?
No. Although you can say, if you look at the Helium McInnes paper, there's various constructions. And there's stability results about how those constructions are related. But, stability itself, I'm not sure. I mean, it will be stable for a while. I mean, you can write stability results for a while because of this relationship with BFS, but that's cheating. I don't know what happens in general.
Okay, if there's no more questions, I think we should thank the speaker again.
I do have one.
Oh, please.
General and vague, but it's because you had made some sort of more general references to this stuff about sort of orientation and orderings and how to make use of them, and you talked about how sort of you had, but then you sort of just made a more vague reference to, well, you want to think about this in terms of time or something.
Yeah.
I was just wondering sort of, if you could maybe expand on more sort of what your hopes were with this directed stuff, or how one might think of these orderings or orientations or whatever in terms of, just sort of not just the pure math, but where you would hope that would go, and what sort of examples you would think of in terms of real world analysis where you get.
Well, there's a big debate going on right now about what's a decent example here. Okay, in terms of applications, particularly with the people at that institute. The obvious thing to think about is a time series. Okay, but if you have a bunch of simultaneous events, you have to figure out a way to totally order those simultaneous events. You have to, there has to be a rationale for doing that. And I haven't seen an example where such a rationale naturally appears. What I'm hoping for ultimately is figuring out the internet. You can look at message passing between various IP addresses. The message will have a time that it goes and a time that it arrives, and source and target IPs. And that's a natural time series because it is controlled by time. But there might be messages arriving at different IPs at the same time, although people would prefer not to think that's true. And in the presence of such an ordering, these Vietoris-Rips complexes are naturally defined as simplicial sets in the way that I said they were. So in particular, they're oriented simplicial complexes. And those oriented simplicial complexes have path categories or fundamental categories. These are objects of higher category theory. And one might want to study there will be persistence associated with these path categories. One might want to study that in order to find out what's a robust execution path or a robust communication path between two different IPs, at various times. But the path category construction it's a fundamental category. It can be made algorithmically on a finite oriented simplicial complex. We have software for that. So the question is, what are we studying with that persistence thing, you know, and what are natural examples?
Okay. What software, he asked naively, works with oriented simplicial complexes?
Well, there's an algorithm. It's based on two categories, one way or another, which constructs the path category from an oriented simplicial complex. It was used initially for studying higher dimensional automata and the execution paths in those. Okay, it's awful software. It's exponential in growth, but at the same time, it's something. So one could hope to use that.
You have a reference you could send on for that?
Yeah, I have an old paper called Path Categories or something like that.
Is that the Misamore paper that you cite?
It's a precursor to that, although he did a lot of work with the idea.
I have one final question for the polygonal path that concatenates.
Mm-hmm.
I see you used it when it gets discrete, you fixate on fuzzy simplical sets, but the flabby pre-sheaves, is that possible to intertwine into the DXY?
Flabby means injective object to me, which also means huge. So, I mean, what we want here are things we can use in algorithms, and I'm not sure I'm seeing that one.
Great, thank you.
Yeah.
Anyways, let's thank our speaker again. I'm going to put the YouTube video of it up eventually. And I think in 2 weeks, David Ellerman is speaking here also on the 26th. Oh, no, the 24th. No, whatever the 2 weeks is. Anyways, thank you very much.
You're welcome. Thank you.
Okay, I'm shutting off the recording.